Before we do that, let me say, think of me as a spokesman for almost a generation of young physicists, and some not so young, who are now really involved in a collection of activities which cuts across, in a way that I really find unprecedented, cuts across condensed matter physics, gravitational physics, quantum physics, computer science, in a really, really remarkable way. I have not seen anything like that in a very long career, incidentally, and I find it extremely exciting that these different disciplines are affecting each other, infecting each other in such a dramatic way. Now, where I come from the discipline of high-energy physics, particle physics, but I don't do particle physics anymore. I think much more about gravity. So I'm going to tell you a little bit about how this idea of entanglement has affected some of our concepts about gravity, about space, about time, and especially about black holes. Okay, so I'm going to get behind this thing here just in case you throw rocks or tomatoes at me. Okay, so what makes quantum mechanics different? Well, entanglement and something else, the capacity of complexity, we'll come to that. But I don't have a whole lot of transparencies here, about 50 of them, no more than that. You think I'm kidding, I do, but I'm not going to use them all. All right, so entanglement. You tend to think of entanglement as having to do with entangled particles or something like that. Well, there's a lot of particles in this room, and they are, you're one, and you are entangled. I know, entanglement can mean many things, but in fact, you're even actually technically entangled. But there's a much larger reservoir of entanglement in this room, much larger than having to do with the particles in the room. It would be here even if the room were completely evacuated and just empty space. It's the entanglement of empty space. What does that mean? How can empty space be entangled? Well, if I were to divide space in half, here you see space has been divided in half by the vertical line there, and I would divide it up into cells. We all know, no, we don't all know, some of us know, that in quantum field theory, the fields in space-time fluctuate. And in fact, those fluctuations can be entangled. If I divide the room in half, I will tell you now that the left half and the right half, their quantum fluctuations are entangled. Here's a picture that shows a region of space divided into two parts and divided into cells. Don't worry about the details of the way I divide it into cells, but those cells are entangled. The green arrow there shows how the pattern of entanglement between the left side and the right side of the room take place. Now, don't worry too much about the details. You might ask, what would happen if they weren't entangled? Supposing somebody could make a partition right down the middle of the room and break the entanglement of both sides. Something very interesting happens. This we've learned over the last 10 years or so forth. The effect on space of disentangling the parts of it would be to disconnect those regions of space. One way to say that, and the way I like to say it, is entanglement is the glue that holds space together. The entanglement of the different parts of space or the different quantum fluctuations is actually what holds it together. Reinstate the entanglement, allow the two systems to become, the two halves of the world to become entangled, and they become connected again. That is a very dramatic new idea, that space is held together between the entanglements of its parts. Now I want to tell you a little bit about black holes. Okay? Let's take two versions of a black hole game. The black hole game simply consists of Alice and Bob. We all know Alice and Bob. Alice and Bob each have a bunch of particles, a large number of particles. They're very, very far from each other. Those particles have never been in contact with each other, Alice's and Bob's. Alice takes her particles and squeezes them down to form a black hole. Bob takes his particles and squeezes them down to form a black hole. We've created two black holes. Those two black holes are disconnected from each other. They may be miles and miles apart. In fact, let's say they're kiloparsecs apart, very far apart from each other. And I've just drawn black holes as sort of lumps in space The gray lines inside are the horizons of the black hole, not very important, the details. Two completely disentangled, I use the word both in a formal sense and a non-formal sense, two disconnected black holes. Now, this is version 2 of the same experiment. This time, Alice and Bob create, when they're close to each other, that's on the left side over there, way over there, Alice and Bob create a whole bunch of entangled particles. Pairs, what are called bell pairs. They create these entangled particles. The black line between the oh, it's a red line in this picture. The red lines just indicate that those particles are entangled. And then Bob puts his half, his share, in his pocket. Alice puts her share in her pocket, and they walk far away from each other, so they're very, very far away from each other. That's the next picture over there. They're not stretching anything. Those lines are just showing that they're entangled, far away from each other, and then take their particles and collapse them into black holes. The result is two entangled black holes. Because the black holes are entangled, here were the black holes when they weren't entangled. Because the black holes are entangled, the horizons become connected. Just like in that first picture I showed you, when you entangle two regions of space, they become connected. When you entangle the two horizons of the black holes, they become connected. Those two black holes are very far from each other, and yet, by virtue of the entanglement, they're connected through a wormhole. Now, there's a very interesting fact here. It's called ER equals EPR. What is EPR? Well, we already heard what EPR is. It was Einstein, Podolsky, and Rosen, and that was the famous paper of Einstein, Podolsky, and Rosen in 1935, who discovered entanglement. What is ER? ER stands for the same Einstein and the same Rosen, who wrote in the same year a totally different paper about another subject, and the subject was wormholes connecting black holes. What we have found, and when I say we, I'm talking about this generation of young physicists, not me particularly, is that the Einstein-Podolsky-Rosen entanglement between black holes leads to Einstein-Rosen bridges between them. That is a very dramatic fact about space-time and the way space-time is put together. Now, you might say, okay, these black holes are very far from each other. I've got one way off, and Alice has hers on Alpha Centauri. Bob has hers in Brooklyn. Can't they go through the black hole, and can't they go through the wormhole and talk to each other when they get through the wormhole? Well, unfortunately not. Here's what would happen to such a wormhole when it was connected. It would start to grow. Here's a picture of it growing. I love this. I love doing this. Oops. You want to see it again? All right. Here's the wormhole. It starts to grow. Because it grows so fast that nobody can go through it. It becomes what relativists call a non-traversable wormhole. The growth of the wormhole is a phenomenon which saves locality. It becomes impossible to communicate through it. But the growth of that wormhole is also related to another deeply, deeply, deeply quantum mechanical phenomena. It's called the phenomena of complexity, quantum complexity. I won't go into it now. Perhaps I'll be asked about it again. But the growth of the wormhole is the growth of the quantum complexity, which is another related concept from quantum mechanics. What I will tell you is we're beginning to see connections between the ideas coming from gravity, the ideas coming from black holes, and the ideas coming from computer science, which appear to be connected in very interesting and exciting ways. And that is my physics lesson for today. Thank you.
Okay, thank you.